Canada's population has grown steadily over the years, influenced by the factors such as immigration, birth rates, and economic development. Understanding and predicting this growth is crucial for future planning in areas like healthcare, education, infrastructure, and sustainability. In this presentation, we will explore how numerical methods, specifically the general and particular solution of a different equation, can be used to model Canada's population growth. By using a real data, we developed a mathematical model and even extended it by adding 20 years into the calculation to predict future trends. So the objectives are, by the end of the presentation, we aim to understand how different equations are used to model population growth, differentiate between general and particular solution in this context, apply the solution to actual Canadian population data, extend the model by predicting population 20 years into the future, and last but not least, evaluate the strengths and limitations of this approach for long-term forecasting.
This is the table data for the population in Canada. It covers a range of 20 years from 2004 to 2023. As we can see, there are increasing population over time. By using the data that we obtained, we formulated the particular solution to predict the future and the past population value. Firstly, we let T to be the number of population in Canada present at time year. Since the rate of growth is proportional to the number of population itself, the equation will be dP over dt equal to Kp. Then we use integration skill to obtain the equation.
Now let's go through the graph. Here we can see the graph showing the population of Canada from 2004 to 2033. The x-axis represent the years, while the y-axis shows the number of people. As we can see, the population steadily increases every year, showing a clear upward trend. To model this growth, we use the particular solution, which is an exponential function based on the equation P of t equal to 319380807 e power of 0.00947t, where t is the number of years since 2004. This equation fits the data quite well, especially in the earlier years, and this helps us to estimate the future and past population. However, the actual population doesn't increase at perfectly exponential rate, which causes slight error in prediction, as seen in our error calculation. But overall, the graph effectively shows that Canada's population has been growing consistently over the years.
Now, we would like to explore how we can predict both the future and the past population of Canada using our particular solution. To do this, we substitute different value of t, which represent the number of years after 2004, into our population equation. For instance, to estimate the population of the Canada in the year 2024, we substitute this value of t equal to 20 into the equation. After calculating, we obtain a predicted population of approximately 38,598,823 people. On the other hand, to estimate the population in the past, such as the year 2003, we use t equal to -1 since 2003 is 1 year before 2004. Substituting this value into our equation gives us estimated population of around 31,637,774 people.
For the discussion part, the first question is, are the values calculated from the particular solution accurate with the actual values? Our answer is no. This is because the predicted population in 2020 is 37,517,661, but the actual value was supposed to be 38,286,038 with a difference about 51,977. The second question is, find the percentage error, if any. To calculate the percentage error, we use the formula of actual value minus the estimated value over the actual value and times it with 100%, and the value turned out to be 0.06%. This low percentage error shows that our data is pretty accurate. The third question is, if there is any difference between the actual value and the value calculated from the particular solution, why do you think it is so? The answer is, the inaccuracy in the results can be explained as the value obtained by using the particular solution increases continuously in a fixed pattern, while the actual population in Canada increases, but not in the same manner as the particular solution. This is because real-life population changes depending to aging rates and also migration. The fourth question is, what has affected the population growth in the past? In the past, the population growth is affected due to the low birth rates, economic strains, and also the lack of healthcare services provided during that time. The fifth question is, what do you think might affect the population in the future? The population in the future might change depending on the birth or death rates, economic challenges, the advancement of technology in various fields, and also changing social values. And these factors can cause a population to decrease and also increase over time.
In conclusion, in this project, we successfully modeled population growth using first-order differential equation and real-world data. By deriving and applying the particular solution to the differential equation, we were able to predict both future and past population values. Our model projected a population of 39,711,142 in 2035 and estimated 31,300,000 and 39,579 for the year 2002. When compared to the actual data, the predictions show a high degree of accuracy with only a 0.06% of error for past estimates. Minor discrepancies may be attributed to real-world factors such as migration, fluctuations in birth and death rates, or external influences like government policies and economic conditions. Overall, this project deepened our understanding of mathematical modeling and demonstrated how mathematical tools can effectively analyze and predict real-world phenomena.
Hello everyone. Today, I am excited to walk you through the Newton-Raphson method, a smart and efficient way to find solution to non-linear equation. So this method helps us to find the roots of equation that are hard or impossible to solve analytically. It uses a formula involving the function and its derivative to improve cases step by step. So here's an example of a function that we're trying to solve. This could come from physics, biology, economics, you name it. We use Newton-Raphson to find where the function is equals to 0. So starting from initial s at 0, the initial s is equals to 1.0. We plug it into the function and its derivative to calculate a new and better estimate s1, which is approximately equals to 0.1726. So this graph shows what's happening visually. We start at initial s at 0 and draw a tangent to the curve at that point, and where the tangent hits the x-axis become our new gas s1. Each step brings us closer to the root, is where the curve touches the x-axis. So let me break down to you what each element means. So S0 is the initial gas, f at 0, f in terms of at 0 is the value of the function at that gas. Then the line uses the slope derivative to estimate new point, S1 new approximation after one iteration. A root is where the fx is equal to 0. So this is a breakdown of the component. With each iteration, we use calculator to leap toward the root instead of stumbling blindly.
The value x right here is actually the x-intercept of the tangent that touch the function x equal to 1. So what we are going to do here is that we substitute the value of x-intercept of the tangent into the formula of x minus f over f prime x. And we do it again multiple times until we get the value that didn't change in 5 decimal places, which approximately 0.55 to 1. Now this is the value that the function f x touch the x-intercept. Now we can understand it better by looking at this graph. At first iteration, we find the value of x-intercept of the tangent that the value of x is used by doing the same method. So we can actually see that the tangent x-intercept is coming closer to the actual intercept of the function. Now that is how we find the x-intercept of the function using the Newton-Raphson method.